Well, welcome everyone to the Sierra Foothills Amateur Radio Club Zoom room. And thank all of you for joining us this evening for a special FSARC tech presentation. My name is Graydon, KC6SLE. I'm the Vice President of the Sierra Foothills Amateur Radio Club. Our presentation this evening is going to be the demystification of the VHF UHF J-pole antenna by Dr. Ed Fong. Before getting started, I'd like to remind everybody, if you have not already, to go ahead and put your Zoom on mute so it doesn't interfere with the presentation. Thank you. And welcome, Dr. Fong. I want to thank you for joining us this evening and agreeing to be our presenter tonight. And if I may, I will have you start out your presentation when you're ready with a short overview of your career and your experience. So, Dr. Fong, the microphone is yours.
Oh, me? Oh, okay. Oh, thanks a lot. Most people call me Ed. Even my students call me Ed. Yeah, I'm Ed Fong here. My normal job is I teach over at UC Santa Cruz, and I basically teach 3 classes now. I teach a RF design class, which is the most fun class for me. But I get the least students. They're all the class that I fill up mostly now is what's called high-speed I/O. I guess that's the in thing. Not wireless, wired. You know, how do you transmit 30 gigabits across a twisted pair or something like that? That's where I get that. I fill the class with. But then, you know, wireless used to be really, really hot, but you know, it changes. Things vary. And then I teach a wire antennas class, and you would think, well, the antennas class is pretty hot. It's okay. Things change, and right now the thing is high-speed interface. How do you do backplane high-speed interface? You know, 30 gigabits per second on a twisted pair, and there's interesting techniques for that we've achieved. But I'll be teaching, in fact, the spring quarter, I'll be teaching my radio class. And that's obviously, being a ham, that's the most fun for me, but you can't say that for everyone else. But so today we're, I gotta hit this. So today we're gonna talk about this antenna. How do you make basically a single band antenna into a dual band J-pole without a whole lot of sacrifices? We're going to talk about this concept I came up with almost 20 years ago. And it's pretty standard. And I'm sure a lot of you folks have these antennas because I've given this several talks at clubs in Sacramento in the past. And so it's pretty popular. And of course, I've given it in Pacificon, and in the past, my students and I have sold antennas at a booth there. Now we just don't have the time. We've got so many orders. We sell about 300 to 400 a month. So you can imagine we sell 4,000 in a year. So we really make a lot. In fact, what you see is the manufacturing room in the back of me right here. That's when the students show up twice a week, and we just go at it. But I typically tune every single one. They could do pieces, but they can't tune it and put it together because it takes a lot of skill for that, just a lot of experience. So they cut wires, drill holes, all the things that they can do, they do. And otherwise, I would have to do them. So they help me out. So that's what we're going to talk about today. This one that's in the ARRL handbook, it's in the Antenna Classics book, it's in the Antenna Compendium 8 and 3, but it was originally published in QST in 2003. That's when we came up with the concept. But I'll give you a little history behind how that came about. It's pretty interesting. So this right-hand side is the QST article from 2003. That's the front page. Then we subsequently did a roll-up portable version. I think a lot of you folks are familiar with that in 2007. That's actually was suggested by one of my students. Hey, you know, this is a really cool antenna. Could you make it portable? And we did that. And then by 2017, actually about 2016, the FEMA kept on bugging me to make them a tri-band antenna, a 2 meter, 220, 440 tri-band that they basically all wanted it all still in a PVC pipe, no radials, single connector. And I said, oh, let me see what I can do. So we came up with this 2 meter, 220, 440 antenna that stands about 5 feet. No, this prototype was a little taller. It's actually only about 5 feet tall, so about here. And that's my daughter, KJ6QXM. Maybe a lot of you guys have met her. She's a bachelor's and master's in mechanical engineering and a master's in electrical. So she's pretty qualified to do this stuff. Oh, and by the way, I hope you guys worked CQ Worldwide over the weekend. Man, was it open? Oh, and I worked 25 countries, which is a lot, for just, I wasn't serious. I was just playing around with my station. And wow, it was open, 10 meters especially. Anyway, so, and we've had to also patent a lot of this stuff. That wasn't my first choice to patent, because a patent costs about $5,000. But we found that the first antenna that we're going to present tonight, a lot of folks start copying it. And that was okay. I mean, that's why you published an article in QST. Where we had to put a stop to it was when people start building it and selling it on eBay, and selling it as the Ed Fong antenna, saying, buy the Ed Fong antenna from us, we're the cheapest. And that kind of bothered me. And it really bothered me when I started getting my students to buy them, and we couldn't find a single one that worked right. They didn't understand the concept of it. How do you actually build? They just took the dimensions, and you guys are probably really experienced RF guys. I'm sure some of you are. You just don't take dimensions. You have to trim them, right? Because you have different wires, different twin leads, different coaxes, quarter inch, eighth inch here and there. And that's how you tune it. At UHF, an eighth of an inch, a quarter of an inch makes a big difference in where the thing resonates. And when you got to get multiple elements, as you'll see here in this talk, resonating, you just can't put it together. You got to put the first one together, measure it, add this, measure it, add this, measure it, add this, measure it, etc. And every time you get a new batch of wire or whatever, you have to recharacterize it. So it's in concept, you can understand it. When you actually build it, it takes a lot of tedious work. And we end up, all our materials now are all custom ordered, custom made for us. We don't buy anything, nothing off the shelf. Even our RG174 is spec'd. It's a special RG174. Otherwise, every time we get a new batch, we got to characterize everything. The dimensions change 1/8 of an inch here, 1/4. It takes way too much time. It's better just to easy ordered from the factory with a certain spec. So the antenna I chose, a dual band. I could have chosen a lot, but I ended up choosing the J-pole. And I'll tell you why I like the J-pole. The J-pole design, no radials. That's really cool. Radials stick out. And I when I was growing up, we used radio antennas. Yeah, they work fine for about a year if it's windy. A homemade 2-meter ground plane. All we used was like number 16 copper wire for the radio. Soldered it on an SL239, flipped it around, and you get SWR pretty well, and it works, but it won't hold up. Anytime you use solder, exposed solder to hold up something is a bad idea. Solder is not very hard. A weld is okay. Solder is very, very soft, as you know, and it kind of fools you that it's metallic, but it's actually very, very soft. So this configuration here, I think, is pretty rugged. There's no radials. The radials stick out, winds blow, and then they eventually fall off. Especially, we've had 70-mile-per-hour winds around here, it's gusts. So I like, and again, the vertical J-pole, I like it because it's a very ideal dipole pattern, much more so than a ground plane. A ground plane is more of a spherical pattern. And what's interesting about it is if you actually measure a J-pole versus a ground plane, it's about 1.5 dB, 1.6 dB higher on the vertical J-pole. And then also end-fed. It's end-fed. Again, I'll describe this here. In fact, I have to show it to you. Yeah, you feed it from the bottom, which is really nice because you can hold it up, just like these half-wave antennas now that you see end-fed HF antennas. Having it end-fed is a real convenience as opposed to being center-fed. See, here's a center-fed antenna. Dipole we built years ago. It's just made of copper pipe, and there's you don't see it. There's an insulator there. That's just a standard VHF dipole, but it's center-fed. It has to be center-fed because center-fed is where you get the 50, 60 ohms or so that you can feed it with coax. It's low impedance. It's high current, low voltage, and at the ends of the half-wave dipole is high voltage, low current, which means that's high impedance, that's low impedance, and that's high impedance. So when it's low impedance, you can feed it directly with coax. But now, if you look at this dipole, it's a great antenna as a dipole, but you got to feed it. That's where the drawback is, the mechanics of feeding it. You got to feed it at 90 degrees with coax. And then you got to support it with a mask of some kind. So this is getting kind of complicated. Here we built this one all out of copper pipe. And you mechanical engineers can tell is, You want this dipole as far away from this mass as possible so that mass doesn't go interfering with your pattern. I can look at this right now. If you were to actually trace the pattern of this, with the receiver, it's going to be directional because this pipe that's holding it up is acting as a reflector. It's going to act as a reflector. You got to get it really far out where it's not going to act as a reflector. But if you got it really far out, this thing won't hold up because, simple, I can give an example of this thing. Here. Simple example. Here's our antenna. Here's one of our antennas. It's end-fed. Here's the connector at the bottom, SO230. I can hold this up with one hand. The weight is just vertical, it's just a vertical force. There's no horizontal force associated with that. But if I have to hold up a dipole so many feet away, because this can't be real close, it won't work. It'll be too close to the mass. It's got to be further out, and the further out, the better. But the further out you get, the more mechanical engineer will take the R cross F. It's got R cross a force times the distance. So if I can hold this up with one hand vertically, but I can't hold it up with one hand horizontally because of R cross F. And you can imagine if I had an antenna on the other end. So the mechanical force that is placed right in that is tremendous. Again, the further you go out, the more force. It's R cross F. It's the force times the distance. And we found that if you're just soldering, using solder for the copper pipe, it won't hold. I mean, solder will hold as piping in your house because it's not outside blowing in the wind. But over time, that solder will crack. We've done this. It will crack because this thing, during the winter, the winds are blowing 40, 50 miles an hour. Eventually, it'll work through that solder and it'll crack. So initially, it will work. So you want something that's very, very durable. And we think that again, no radials, very close to ideal dipole, end-fed. Being end-fed is very important physically. I mean, electrically, you just want a half-wave dipole, but this is a good way of achieving it. See, so if you look at this photo here at Sutro, and by the way, you guys in Sacramento, KRON broadcast is up here. You guys should start receiving it. Now, they have an extra antenna. It wouldn't surprise me if you guys can receive channel 4 KRON digital TV now. They just, I monitor all this stuff at home. They just are on their new transmitter and new site. It wouldn't surprise me if you guys can see it now. Before it was a very poor antenna they were using. But anyway, I took this picture about 3 years ago. Sutro, Mount Sutro, you guys in the Bay Area, you know that. That's where the Sutro tower is at. This is one of the other towers on the side, commercial one. You notice I took this 3 years ago. I wish I would have had a picture of it 30 years ago. There's not a single antenna here that's got ground radios. You notice? They're all verticals. People have learned over the years, you go with a J-pole design that requires no ground radius. And what's the disadvantage of a J-pole design? Of course, it's 3 1/4 wavelengths tall. A ground plane is only 1/4 wavelength tall, and then 3 or 4 radials of 1/4 wavelength. But then it's got wind load, tremendous wind load. So at VHF, it's pretty practical. Just have a half-wave J-pole, which is half-wave and a quarter-wave matching. Here, I'll show you. So J-pole takes on this configuration. Here's the half wave, for 2 meters, 37, 38 inches. So normally in the old days, we would feed it in the middle, but I just showed you in the middle, although it works, it's just too impractical. You need to feed it at 90 degrees and you're going to have to hold it up. You're going to hold it up with something, and it's going to act as a reflector. And just physically the torque at that node where it's held up by the mass is tremendous. So if you can get a J-pole going like this, and I'll explain to you how it works. The point is it's 1/2 wave and a 1/4 wavelength matching stub. That equals 3 1/4 wavelengths. So it's tall. It's 3 times taller than the ground plane. Ground plane would have been just 17, 18 inches, and then with ground radios. But we know over time, it just does not hold up. We used to spend a lot of money on repeater antennas that using, again, a ground plane design. And if you're on top of a mountain where it's really, really tough, they just fall apart after a while. Then eventually we start getting the Phelps Dodge ones. Those are $1,000 a piece. They're welded. They're really strong. But if you want to make your own, you're better off with something that's just vertical without radials. So we liked that. And the other thing is, when you make a J-pole, and we made it originally out of just twin lead here. It's just twin lead. This is just originally 300 ohm twin lead. So it's, pretty inexpensive. I think we do it a little differently today. So hang on, let me go back here. So when we made it out of these, that antenna we just showed you, and I first saw it with Denny Monticelli, AE6C. Some of you folks might know him. He showed it to me back in the 2000 probably. He said, "Hey Ed, what do you think about these? I'd never seen a J-pole design like this." He said, "Try it out." He just made it out of Radio Shack twin lead at the time. I took it home, and I was active on 2 meters, and it worked really well. I thought, "Hey, this thing works pretty well." And he gave it a roll up for him, so it looked something like do I have a roll up bunch? He was playing around with it. I worked with him at National Semiconductor. He eventually became the chief technical officer. He just gave it to me like this. Just kind of roll it up. He goes, "Take this home and hang it up and see if it works." And it worked. I liked it. And so I said, we should make a base station antenna out of it. So I started looking at the PVC pipe, sticking it into a 3/4 inch PVC pipe, putting a connector at the end, an SL239. Pretty good base station antenna. And single band, but what we want to do is make it dual band. Because by 2000, if you guys remember, all the dual band handy talkies were coming out, dual band mobiles, and a lot of us. I had a G6 antenna, single band. Larson makes this a G6, single band, but all these dual band radios, and by that time, a lot of the 2 meter repeater pairs were running out, so UHF started becoming really popular. So a lot of folks say, "Hey, we need a good antenna without spending $200. We need a good antenna. We don't want to spend $200." And what people notice is, but my VHF antenna kind of performs at UHF. And what do hams do? What's the first thing to do to check an antenna? They put an SWR meter on it. And the SWR is okay. It's not great, but 1.5 to 1. A lot of folks didn't understand that. Most VHF or any antenna, and you take the third harmonic of it, the first odd harmonic, it will resonate. So to simplify this, if you make a 100 megahertz dipole, and you get one of these nano, VNAs, which I have one right on my desk here. You guys got to get one. These are great. For $100, these things are great. Learn how to use it, and boy, you can do all kinds of filters, antennas, you name it. You get one of these, and you say, "Hey, my 100 megahertz dipole also dips at 300, 500, 700, 900. That's how antennas work. If you take my antenna class, you're just adding a half wave section to it every time. It's another way of saying you're going around the Smith chart once, 360 degrees. If you do that, you come back to the same spot. So basically what it says, without all the math, 100 megahertz antenna will also resonate at 300, 500, etc. You can apply that to a VHF antenna. And this was no accident that the FCC assigned this. It makes it easy. If you have an antenna at VHF, what's the first third harmonic? It's UHF. 150 times 3 is 450. It won't fall exact, but not bad. Close enough. Because if you were to take 145 times 3, that's 435. So 146 would be 436 or so, 437. So it will work. It will work. At least it will work in terms of matching. But what folks notice, and I notice this very quickly, when I says, "Hey, let me try my VHF antenna at UHF," it doesn't work real well. That's the problem. If you really analyze it, you get this pattern here. This is an EasyNet simulation. You'll get the same output with ADS, Hobbies, any of these RF simulators. In fact, EasyNet is free now. Roy Llewellyn retired, says, "You guys can have it free." And it's a pretty good program, let me tell you. So this is the free space. Good to compare antennas in free space. So this is the sky, this is the earth, and this is sea level right here, sea level. So at the fundamental, so this is looking into it. So looking at the top, the sky looking at the top, it'll be like a donut, 360 degrees. But if you're looking at the elevation angle, which is here, The pattern is, here's the fundamental. So it looks like a figure 8. A great pattern when you think about it. It's a half wave, because here's the sky and it forms a node right up, because you're not talking to anyone up here. You're trying to talk to people out here. It just does the right thing. It peaks at sea level. And this is the Earth, but it doesn't peak up at the sky. See, that's where the ground plane differs. The ground plane is more like a sphere. You don't want to be transmitting in the sky, I mean, unless you want to, talking to an airplane or something. But if you're usually talking to someone terrestrial, you actually want like this pattern. A good vertical half wave fed dipole works quite well. And I think if you antenna guys up, you know that if it's done properly, it works quite well. The problem is not, I said a third harmonic, which at VHF will be UHF. Now you simulate the same 2 meter antenna on EasyNet. And here's the pattern now. Here's the sky. Here's sea level. It covers 360 degrees, but most of the energy is going up into the sky. In fact, if you quantify it, it's about 75%. 75% of the RF, if you feed a VHF antenna, UHF signal, points up into the sky, and only about 25% of it remains. I don't want that. But why do I want my 25-watt mobile look like a 6-watt mobile? You want to look like a 50-watt mobile. You're going in the wrong direction. So that's what people notice. Yes, the antenna will resonate, but the energy is going in the wrong spot, mainly into the sky. So what can we really do? Oh, by the way, I can explain this, why it does this here. You can explain this without the math of why it does this. So hang on, one more thing I gotta explain to you. Smith chart. So in order to understand this, you have to understand basic Smith chart. Not in detail, just basically. Here's a Smith chart. And what the Smith chart represents is it's 0 ohms here. And if you go, it represents a full half wave. It doesn't have to represent a full wave because it's a wave is symmetric. It just has to represent the half. So if you go 360 degrees, you return back. It's a half wave to the same point. Opposite phase, but to the same point. But what's really interesting is if you go a quarter wave, what happens when you go a quarter wave? Well, what the Smith chart says is when you have a short circuit one end, and you go a quarter wave, in the case of UHF, that's 5-6 inches. In the case of VHF, it's about 18-19 inches, depending on what material. The short circuit would also look like an open circuit. And similarly, an open circuit will look like a short circuit. So let me give you a good example of that. Let me get a quarter wave stub. See, the good news is we're in my working room here. I got all my stuff right in back. So we cut a bunch of these quarter wave stubs. You'll see this. That's just an RG58. It's about 5 inches. That's a quarter wave at UHF. It's not 6 inches because it's in the coax. In the coax, it's going to be less because the speed of light is slowed down in the coax compared to air. Right? In air, a quarter wave at UHF is about 6 inches. In coax, it's about 4.5, 5, depending on the characteristics of the coax. I always show this to my students, first year students. They're not hams. When you show them this and say, okay, open circuit, right? Open circuit, no tricks, it's open circuit. So what's the impedance at that side? Most people say, well, it's open circuit. And I try to really shake them off of that. That's DC, it's open circuit. AC, it is not. From a signal point of view, this is 5 inches. So this is an open circuit right here. If you go quarter wave, which in this case is at UHF, will be about 5 inches. You go 5 inches, you go around like this, it becomes a short circuit. And similarly, a short circuit, if you short one end, it becomes an open circuit. So you guys are probably familiar with this if you make harmonic filters out of coax and quarter wave stubs and things like that. So we use that trick a lot, or technique a lot, in antenna design and matching. So basically, I'm going to explain to you the 2 meter J-pole. Again, it's a half wave antenna. You could have center fed it, but we just explained to you why you wouldn't. It's just mechanically not a very good way of doing it. So you need to end feed it. If you can end feed it, then you can have it vertical and end feed it. And like what I demonstrated, you can just hold it up from the bottom. The force involved in just a vertical force is much less than if the thing had horizontal force. Horizontal force is terrible. So then what you're stuck with is, okay, when we center feed it, it's low impedance, which is high current, low voltage. The ends are high impedance, and that's how the antenna radiates. It's going to be high voltage, low current. Right? The power is the same throughout the antenna. So it's high voltage, low current. Well, if it's high voltage, low current, that means it's high impedance. So again, if you go from a low impedance, a quarter wave transmission line, it's going to be a high impedance, just like what the Smith chart says. So what do? Here's a high impedance. I would love to feed it there. Certainly 50 ohms is not a high impedance. You need in the thousands of ohms, in the thousands to make it equivalently high impedance. So you go back to this quarter wave stub I was telling you about. At 2 meters, it would be, with twin lead, it would be about 16.5 inches. Again, it's not 18 because it's in the twin lead. The twin lead was slowed down the speed of light by, not depending on the material, 10%, 15%. So that it comes from the formula, the speed of light C is equal to F lambda. C is equal to the frequency times the wavelength. So when you calculate what the lambda, the wavelength is in the twin lead, you don't use C equals F lambda. You don't use C for the speed of light because it's in the twin lead. You use a correction factor, whatever it is, multiply by 0.8, 20%. It slows down the speed of light by 20%. So if you do, C equals F lambda, where C is not 3 times 10 to the 8th meters a second now, it's more like 2.5 or so times 10 to the 8th. Then the lambda equals, the frequency is the same, so C is equal to F lambda. The lambda then won't be the famous 18, 19 inches for 2 meters. It's going, you worked it out, the math is going to be less. It's going to be about 16.5. So that's quarter wave stub in our twin lead. It's going to vary. Quarter inch here, half inch there, depending on whose you use. You've got to characterize this to build this antenna because we're going to use this as a matching network. How does it match? Because we know when we short the bottom, as you go up 1/4 wavelength, what the Smith chart says, it becomes a high impedance. That's how you match the high impedance of the dipole. That's how a J-pole works. And I'm sure you guys, you've built ones like this, but I'll tell you, it's the beauty of this is this, it's end fed, that's great. It is taller, but again, at 2 meters, you're okay. At UHF, you're great. It's only 6 inches for every quarter wave. So the thing's, 18 inches and you get a J-pole, that's nothing. The concept applies to HF a little bit. So you guys know at HF, unfortunately, then you suffer, right? You need that extra quarter wavelength. It's end fed, but you need that extra quarter wavelength. Sometimes not always available. So, but this technique is really advantageous for VHF and UHF. But the other thing you notice, it's kind of a bonus. It's a DC short. Remember, you short this end. So it's a DC short. Why is that a bonus? You don't need a lightning arrestor. How can you beat that, right? It's, you buy these lightning arrestors, 30, 40 bucks, a commercial one about $100, $150. If you want to go clear on up to UHF in a commercial, that's a little bit more expensive, but you buy a cheap lightning arrestor from MSJ, it's like 50 bucks. Why even spend 50 bucks if you don't have to? What does a lightning arrestor do? Usually they're filled with gas, and at a certain voltage, if there's lightning around, it shorts it out. You don't want the antenna to hold charge of any kind, because if it does, it'll burn out your radio, or potentially burn out your radio. Here, you can't burn out your radio. This is ground, shield, and the center conductor. It's a short circuit. Now, it's not a short circuit at the resonance. It's a short circuit everywhere else, or most places, enough places where this can't hold charge. It's great. You don't need a lightning arrestor. So the lightning arrestor people hate the J-pole folks, right? Because again, you look at this photo again. I can't, and it's 3 years ago. If I had a photo of this taken 30 years ago, you would have seen a lot of ground plane antennas. I know I used to hike up there when I was a young ham in the 1960s. It was a standard antenna that everyone used. It's a ground plane. Ground plane's open circuit, so you better have a lightning arrestor. Unless you want to blow out radios, because radios can hold, most of them we've tested, we've burnt out enough, about 40 volts. They'll hold about 40 volts. That's about it. Otherwise, you got to discharge it. Otherwise, and we saw this problem with the Red Cross that I was the technician there. I said, we blew out that radio. I go, what's going on here? You guys are blowing out your radios. That's because they didn't have lightning arresters. And the other problem is they had the transmitters too close, because they would go 50 watts and the other VHF antennas are 5 feet away. Of course, eventually you'll burn out some front end. But yeah, there's again, the technique I'm showing you today, the J-pole does not need a lightning arrestor. It is taller, 3 1/4 wavelengths, but it works quite well. And I showed you the pattern, really nice ideal pattern. So, again, people have implemented this basic idea of a J-pole in various ways, very clever ways. Here's a copper J that really popular a few years ago. I don't think you see this as much anymore at the swap meets. Too expensive to build, copper pipe like this with end caps and then a T, an elbow, couplers there. And one time it was cheap, but boy, you go down to Lowe's or Home Depot and price out the copper of this, it's over $40, $50 now. It wasn't years ago, but it is now. So it's just not an advantageous antenna to build. A good antenna is inexpensive, affordable, functions, doesn't need extra things like lightning arresters, waterproof, weatherproof. That's a good antenna. See, so like we've built some of these. We've built all kinds of antennas here. That's this one here. We've built the copper J. It works pretty well. So it's the same principle. That here's you make the transmission line in air. So this is going to be taller than the one I just showed you because it's not in twin lead, it's in air. So yeah, this one probably is about 18, 19 inches. And then again, it's a short circuit at the bottom. This is a short circuit. So you go about 2 inches and you'll find a 50 ohm point, right? This is infinity. That's a short circuit, 50 ohms. Well, 50 ohms is probably closer to the short than to infinity. Turns out that 1.5 inches, you have to play around with it, tap it off, and you get your little nano or rig expert or whatever, and find that tap point. And again, what we've seen is at VHF, it's not a bad configuration, but it's pretty rugged too. It's all copper pipe. Just it kind of looks ugly. It starts oxidizing after a while, and pretty expensive to build. That's why it wouldn't be my first choice. But more importantly, it doesn't work well at 70 centimeters. And I know I said, but shouldn't it work? It's 146 megahertz multiplied by 3, with the exception of making sure things scale, that your other components still work. It will work at the third harmonic if your other components still work. Well, the problem is this. We found that at UHF, calling that a transmission line is getting hard, right? It's too far apart. It's almost 2 inches apart, and a quarter wave at UHF is only 5 or 6 inches. So the problem is it doesn't scale, right? It works at 2 meters, but at UHF, it isn't transferring the impedance very efficiently anymore because this transmission line it's not very ideal anymore. At 2 meters, it's okay. 2 meters, 18 inches for a quarter wave, and this is 1.5, not quite 2 inches. Is it a transmission line at 2 meters? Yeah, probably good enough. And I would say, yeah, good enough. It'll work. It will work. I mean, this idea that you jump across open space here, again, we found that surprisingly acceptable at VHF, not acceptable at UHF. That's not scaled. It's wrong polarization. It's almost 2 inches. And that's a lot. It's almost 2 inches, and a quarter wave is 5 inches, 6 inches. Too much of it's radiating horizontally. So my rating on this antenna is it's expensive to build. It works at 2 meters. It doesn't work very well at UHF because of these dimensions. So, by the way, I want to explain this to you. You see in this pattern, and we're trying to get rid of this pattern. Can you make a standard J-pole so that both the VHF and UHF patterns look like this? Then it'll be ideal, right? An intuitive reason for why these lobes why are these lobes there at the third harmonic? It's pretty easy to explain. What happens is when you feed a VHF signal here, it's going to be short circuit here, so high current, low voltage. As you go up this quarter wave stub, you start getting higher voltage, but low current, because it's transforming from 0 ohms to infinity. Now at UHF, let me show you here. I'm going to jump ahead a little bit. At UHF, the waveform looks like this. It's 3 times the frequency. For a quarter wave at UHF, it's going to be about 5 inches. Another quarter wave would be another 5 inches, and another 5 inches. It reaches the peak again. The difference is at UHF, you used up an extra half wave. You've gone around the Smith chart once, and then you start from here again. So we'll work fine here. So what that says is it does peak at the supposedly at the same point. So it works. The matching works for both 2 meters and 440. Now, that's the matching part. That's why you get the reasonable SWR. The problem is at UHF, this would want to see a half wave. Right, so let's go back here. At UHF, we showed that pattern. It wants to see a half wave up here. It doesn't want to see 37 1/4 inches. It wants to see about 11 to 12 inches in that range. And if you did that, the antenna would work, but then you would lose your VHF. But what happens here when you put a VHF antenna and drive it with a UHF signal? We showed that it matches up to here, and it would like to see about 11 to 12 inches, but it doesn't. It sees 37. So what happens qualitatively is you drive this element, you perfect match, it goes, it's perfect, perfect, perfect. And I would like to see it, if I want that nice figure 8 pattern, the nice dipole pattern, I've got to cut it. I've got to cut it off there, but it isn't. So the currents continue. If the currents continue, the pattern will start lifting. It'll start lifting. That's why you get that. The currents continue, it lifts, 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 and it forms these lobes. That's not what you want, unless you're trying to talk to an airplane or International Space Station or something like that. But for typical communications, you don't want that. And then rather what's left is this 25%. And that's pretty severe. It was 30% loss, it was 10% loss or something, that's okay. But when you start losing 75% of your signal into the sky and you're only left with 25%, that's not good. That's not good. So I will explain that, and here's another version of the dual band antenna. So we're convinced that that's not a dual band because the transmission line that you form with the copper pipes is just too wide. So it's very inefficient at UHF. At VHF, apparently, I was surprised at this when I tested it out. Proof is in the pudding. It does work. That actually does act as a reasonable transmission line when there's 2 inch spacing at VHF. Now here's another attempt at trying to dual band it by arrow, and I didn't build one of these. I figured, for $50, it was good to just buy one and test it. And that's exactly what we've done. We just buy it and have fun testing it. Well, the way arrow tries to get dual band out of it is like this. You say, well, we have a J-pole. Explain that for 2 meters. They put another element here. So at UHF, it resonates like this, the 6.5 inch J-pole. And so UHF J-pole is the 19 1/4 inch and the 6.5. In the 2 meter J-pole, this is 57.5 inch with this 19 1/4 inch. And it's actually very clever. They've put it into one SL239 connector because they all resonate. And we tested this out, not bad. I mean, I think they patented this. They patented it, and it kind of works. I think it's an improvement, certainly. And why is it an improvement? Because at VHF, again, this won't resonate at VHF, but at VHF, you get this 19 1/4 inch piece, and then the J part is just 57.5. And at UHF, you get this 19 1/4 with a 6.5. So the UHF antenna is here, the VHF antenna is there, but it's only through one feed point. So what's the catch here? The catch here is if you see both low impedances at UHF, both here and here, and let's just assume they both have a good match. They might not, but let's assume that. And you're feeding it here, what does that say? If it's both has a good match, half the energy of your UHF signal going to here, which is good. It's a J-pole of the right size. The other half will go in here because it also has a low impedance to the UHF signal, except it's got the wrong pattern. The one that goes, the amount of signal that goes in here is just right. It's just an ordinary UHF J-pole. But that only accounts for half the energy, assuming that they both match equally. They might not be, but assuming just that they match equally. The other half of the energy will go here, but that's UHF, it's the wrong frequency. So in that part, you will lose about 75%, and you wouldn't lose any of it here. So you still lose, of the 50% that goes into here, you still lose 75% of that energy. So bigger half, it's a few dBs. It's still not ideal. Now, the other antenna that's pretty popular, you can build it, it works. You take the J-pole that we drew, and you just short the top. It does nothing. As far as I'm concerned, they call it the Slim Jim. All you've done is did this, and you solder the tips together. We see no difference, not even in bandwidth, certainly not in SWR. It doesn't make a dual band, no more than this antenna, but it doesn't seem to do it any harm. When we did this and did a bunch of experiments, it still worked fine. It didn't do much to it. So how do you make a dual band? We tried a lot of things. And again, I couldn't use any fancy capacitors, didn't need any fancy inductors. You start doing that stuff, then you're not for the general audience. You got to have something simple that someone can look at, and they knew some basic knowledge, they could build it. And I go through step by step in the article. You get this working, and then you add the UHF section working. And all this time it assumes that you have a network analyzer, or at least an antenna analyzer. And then you add the stub, and then you add the Zen part. So let me explain how we did it. So hopefully by this time I've convinced you that the matching looks like this at VHF, the waveform, voltage waveform looks like that. At UHF, it takes an extra spin around the Smith chart, but it still peaks up at that node. So let's take UHF. So UHF, it sits here in high impedance, and it matches this 11 1/4. If it's lower frequency, it's 12, somewhere around 11 to 12 inches, depending. So it imagines not here. So it's just a half wave. So yeah, it'll match and it'll work. But now, how do you add the VHF into it without affecting its performance? Again, that Smith chart thing I showed you about the opens and shorts. Every quarter wave is an open or short, open or short. You short, again, a quarter wave piece of coax, RG174 in our case, and at 4 1/4 inch. Now, this type of RG174 we have is a pretty high velocity factor. So instead of 6 inches, 5.5 inches, it shrinks it quite a bit inside the coax. And the way you do it is you short one end, and you measure the other end with a network analyzer. You start trimming it until it resonates to where you want, 446 or whatever, because it will read an open circuit. If you short one end, it's going to be an open circuit at that frequency. Because if it is, if you add it in here, you solder the center conductor, remember the top is soldered together, it will see a high impedance. Not only sees a high impedance at UHF, it's a quarter wave step only at UHF, not at the other frequencies. So at UHF, this kind of blocks everything out. It disappears electromagnetically, not physically, but electromagnetically it disappears. But at VHF, you see everything because that doesn't resonate anymore. It's 11 1/4 inch plus 4 1/4 plus 17. And lo and behold, you add that up, that's a half wave dipole at VHF. So when this signal goes through, here, this lower signal, lower frequency signal, 146, it sees this whole antenna with no resonances. But if the UHF signal, which looks like this is a quarter wave, and another quarter wave, it matches right here, it would like to see only the 11 1/4 inches right here. You stop that by a quarter wave stop. You short circuit it here, therefore it would be an open circuit, but only at the 446 megahertz region, wherever you tune it to. So there you have it. So at UHF, it just sees this. At VHF, it sees the whole thing. So how does it work? Do we measure data? Yeah, and here's a roll-up version of it. We just had to be fancy, put a BNC connector on it. We had to make sure it fit all in one twin lead. We cut these little slots here for the electromagnetics, but then they're very, very small cuts. Otherwise, the twin lead won't hold up. And then we put heat shrinkable tubing over it. So that's kind of the portable version, same concept. So one thing I got to mention. So one is designed to hang off a tree branch or something in an emergency. This other one is designed to go into a PVC pipe. So remember I was mentioning your velocity factor. If you hang something in air, you use the formula C equals F lambda. C you can use 3 times 10 to the 8th meters a second. That's basically the speed of light in air, more or less. But if you put it inside PVC pipe, like what I've done here, I think most of you would know. There's no way the PVC pipe speeds up the speed of light. It's got to slow it down. Anything you do to electromagnetic wave slows it down. There's nothing we know how to do to speed it up. So you cover it up, you put it in a pipe. Well, apparently it slows it down by about 5%. Is what we can measure. How do you know that? When you slip this into a PVC pipe, all of a sudden the resonant frequency goes down. It goes down. Because these elements look longer wavelength-wise because C equals F lambda, the speed of light now is slower in the PVC pipe. So the difference is this, same frequency, 2 meters, if you do a roll-up, which is designed to operate in air, as opposed to the space station antenna, which you got to slip it into the PVC pipe, the difference is about 2 inches, right? Watch this, 17, 18, 15 and a quarter, 16 and a quarter. It's about 2. I mean, it's a little bit in other places too, but I just don't mention it. It all adds up to 3, a little over 2 inches, not quite 3, 2 inches difference. So if you operate in air, the antenna is going to be longer because of the velocity factor. If you operate in a PVC pipe, it would be shorter because C equals F lambda and the speed of light is slowed down. Then we tried a bunch of PVC pipes. You know, when you cover it up, are they all the same? Obviously, if some PVC pipe had lead base in it, forget it. It's not going to work. Don't paint it with lead-based paint or metallic particles. But we found that the Lowell's pipe was really good. The 3/4 inch PVC pipe used to be cheap. Now everything's all expensive. It's about $6. I think maybe it's lower now, but it's expensive. It used to be like $1.69, $2 before COVID. But you can also test other pipes. A student of mine did a correlation between the effectiveness of radomes or covers for antennas, and it correlated it with heating up in the microwave oven. So if you ever think about it, you say, is this good or bad to cover up my antenna from the weather? Throw it in the microwave oven for about 5 minutes. If it gets warm, yeah, you're right, not going to work. That means it absorbs RF. But if it doesn't get warm and stays there, it's probably pretty decent. And we found that a very strong correlation. So we find that Lowell's item 23990 pretty stable. You can put that in for 5 minutes, it doesn't even get warm, which is good. That means it makes a very good cover for an antenna or a radome. And that's what we use, cheap and it's effective. So here's how the antenna performs on an 8591 spectrum analyzer. Here we go. Here's the 2 meter J-pole, but at UHF. Point is right about there, it's just a reference. But if you use our technique at UHF, DBJ1 at UHF, boom, that's 10 dB per division. That's 6 dBs. Just exactly what one would predict. Because the propagation programs predict about 6 dB. So what we actually did was we started measuring it, not just by a spectrum photograph, but we looked it up at National Institute of Standards and Technology. How do you measure antennas for an official data sheet? Well, you see around when you get the recommendations, in order to get a real accurate data, you need more than 1 point. In fact, what you would recommend is 5 points on a rainy day, same setup, 5 measurements on a foggy day, and 5 measurements on a sunny day. Makes sense. So 15 measurements, 5 on each day, and take the average of them. And here's what we did. I didn't do all of this. I think one of my students did a lot of this. I showed him how to do it. But here we go. I saw the antenna range. We use a standard antenna range about 50 yards apart. And it sets up pretty easy. It's got power on both ends. So we found that with a quarter wave mobile, we had about, I think we're doing handy talkies here, actually, about 5 watts. You stand about 50 yards away, you get about minus 24.7 dB on the spectrum analyzer. If you substitute a quarter wave ground plane mobile, you know, at 18, 19 inches at each, just replace it with a rubber duck and a handy talkie. Terrible, absolutely right. loses about 6 dB. So rubber ducts, unless you're in a strong area or working through a repeater, not advisable. It's only about 25% efficient. So you say, I want more power, I want more power. No, you probably need a better antenna. You see your improvements much more. So what we replaced it with was a J-pole versus a ground plane, quarter wave mobile antenna. Now, you take 15 measurements, it is quite a bit better, right? Minus 24.7, all of a sudden it's minus 23.34. That's not quite 6 dB. Yeah, not quite 6 dB. But you know, 6 dB is a lot. That's 4 times the power, 4 times the receive ability too. Whoops. And so when we use the VHF, J-pole, UHF, it's pretty bad. Minus 24. Oh, hang on. I'm sorry. This is VHF. So let me go back. This is minus 24 is the reference. Rubber duct loses about 6 dBs. So a standard J-pole, it's about, like I said, about 1.5 dB improvement. Minus 24.7. It's just only minus 23.34. And what we notice is our dual band J-pole, not bad. It compares to a standard VHF J-pole. And I'm pretty confident of these measurements because we took 15 of them. I think that little stub causes a little bit of loss. So on an average, if you take 15 measurements, and I didn't take these measurements, I trust my students did it correctly. And when you took the average, sure enough, it's a little bit worse than a standard J-pole. So we lose about 0.1 dB, maybe 0.134 dB or so. It's not significant. 0.1 is just usually not noticeable. It's measurable, but not noticeable. So it performs quite well. But how about at UHF? So we do the same test at UHF. Here's a quarter wave mobile at UHF. Of course, UHF, the propagation loss is a little higher, so it's about minus 38.8 dBs. Rubber duct in the same location, minus 41.3. Maybe 3 dB, but certainly not 6 dB worse like in VHF. It's worse, but not that much, 3 dB. And what I find is actually you can even do better. Some of these aftermarket antennas, and depending on the chassis, you can get it to pretty low, you know, minus 1.5 dB or so if you really play with it. But typically, you lose about 3 dB on UHF. I suppose the VHF, you lose about 6 dB. That's quite a bit. So at UHF, we use a standard J-pole at UHF, which is exactly what you don't want, right? The SWR is good, but remeasure it. It's minus 45 dB. It's 6.2 dBs off. No. That's 6.52 dBs off. Lower. Minus 38.5 as opposed to minus 45. So what that says is you don't want to use a VHF antenna at UHF if you don't have to. I mean, the good news is it doesn't blow up your radio. The bad news is it just doesn't work. So take your pick. What you want is one of our antennas, that little stub that blocks the rest of it. We put ours in and wow, it almost all came back. Minus 38.9 dB as opposed to minus 45. It's a good 6.1 dBs better using just that little stub, which goes to show you it doesn't have to be complicated, but you got to know what you're doing. If you know what you're doing, it really does work. So that's with all the measurements, and I'm pretty confident these numbers are good. So here's our lab here. This is taken back in 2008. We used to use an 8753, so a lot of you old timers recognize that as the HP network analyzer before super microcomputers came on board. And, you know, they offer now the 5062, which is actually a full computer here with hard drive and all kinds of memories, and you can control the software, and rewrite it. And it's only they try to keep the looks the same so you get familiar with the knobs. And when you open this up, it's got a bunch of boards in there, and it looks like a piece of test instrument. You open up this, it looks like a computer. It's a computer i5 board, and then the interface is this front panel, which has all the microwave chips and all the microwave interface. It's a pretty good unit. I like it. We've had it for about a couple of years now, and we still have the old one. The old one's just a lot heavier. It's not. It's got a microcomputer in it, but it's not a computer. So it's quite heavy. It's got CRT too. This is LCD. So that's how we make our measurements. So some folks look at it and say, "That stub. And what have you added? You added the stub. How does it behave? You've got a network analyzer? Show us. Well, that's how it looks. It's not infinity at a short. I wouldn't expect it to be, because if it was infinity, I can use it as a duplexer. Coax is not that high Q. It's better than nothing, but it's not that high Q. It sits around here, certainly higher than 50 ohms, high, but not infinity. It doesn't have to be. And maybe that's what counts for the losses, right? It isn't infinity. That piece of coax is lossy because it doesn't match. And it's pretty stable. I put my hands around it. You know, this thing, I put my hands around it. It's interesting. At resonance, it's pretty stable. It's right about there, 445. And then for 146, remember, it has to act like a piece of wire at 146 because it's not resonant. So I looked at it at 146. It kind of looked like this. And we swept it. Pretty close to an open circuit, not exactly. And you're really not concerned about all this stuff, because that's not where you can operate it. And by the way, that's a piece of wire, just a bare wire. Remember the other ones, it's interesting. It's insulated with coax, while this is a wire. Well, where the wire stands is right there, slightly capacitive, open circuit at 146. So you take this mark here, take that mark there, they're pretty close. They're really, really close. Now the rest of it's different because one's coax and one's a straight wire, but at the resonance, it's pretty close. So see, here's the antenna hanging on my roof. It's been up there for 2002. Hey, it's 20 years now. I've taken it down a few times to readjust the block and everything, but it works. It works well, and it holds up very well. And you know, it's all curves all over the place. So when the wind blows, it doesn't care. It just blows around. It's aerodynamically, coincidentally, it's pretty aerodynamically designed. Let's see. And here's the roll up. We sell it like this. We sell it like this. And here's the antenna. And we sell it with the adapters, BNC. Then there's a BNC to SMA male, and then that flips it off, flips it around for the Baofengs because they use the other connector. And then we had these extension cables made. These are RF extension cables. Actually made of a special RG174. But this is male and female, so you can plug that right into there to extend yourself. So let me show you how we raise our, here, show you another thing. So I'm done with the talk. We have other talks I've got on how to get gain out of a collinear. And again, at UHF, it's pretty practical. At VHF, it gets pretty tall. You guys probably know this, you know, high gain VHF antennas get pretty tall, no exception here. Then I also give another talk on how do you make the tri-band antenna that was published in 2017. What's the principles behind that? At this point, how about questions? Any questions? I'm open to questions. That's my hour talk. Hope you guys learned something.
Thank you. This is great in KC6 SLE. There were some questions that came up on chat. I'll let the people ask that question if they'd like to. But one of the questions was ABS versus PVC.
Don't know. You can try it. Yeah, that's the gray stuff, right? It's the gray stuff, black gray stuff.
Yeah, it's normally used for drainage pipe or sewer pipe.
Yeah, I don't. Does it come in but that doesn't come in 3/4 inch though for sewage pipe.
No, it does not. You'd have to have a bigger diameter, but it would be convenient for mounting on vent pipes on houses.
Yeah, I don't know what the velocity. I never thought of it so big because that comes in 2 inch, right? Typically, the smallest diameter would be 2 inch. I don't know. Someone should try it. Well, just put my antenna in and see what happens. And also, I don't know what the contents is. Just pick up a piece, put it in a microwave oven for 5 minutes and see if it gets hot.
Okay, great. Thank you. The other question I wrote down was the question, they wanted that part number for the Lowe's PVC pipe again.
23990. I'll send that again, 23990. But if you guys, night antennas, if someone comes down here, like, by the way, you guys know the swap meet's back on. We organize it. The Foothill swap meet is back on. I hope you guys know that. So our first meet would be April 16th, which is the third Sunday of the month, because the second Sunday is Easter Sunday. We had to change it to Sunday because West Valley Junior College was not available. They've got their farmers market on Saturdays. I think we'll attract a lot of folks. I know a lot of you folks come down here because I see a lot of you folks.
Well, that's great. So at that point, let's just open it up for questions.
Yeah, open up for questions. Sure.
I have a question.
Sure.
I have a Baofeng triple
A tri-band?
band. Tri-band,
UV,
thank you.
UV3 times, the UV5 times 3 is what you have.
Yeah, and I was wondering, you were talking about its end-fed, and I would assume it would be, PL259 or whatever.
Right.
And
Correct.
would you have a connector? I mean, I don't think the Baofeng connector is a typical normal radio.
Yeah. So what interfaces to the antenna is one piece. At the end of the other coax, what you need is your Baofeng takes one of these. That will screw right in.
Okay.
So what do you need? And we sell this, we sell the adapter for it, because if you go to any base station antenna, it will always be SO239. That's pretty standard.
Right.
And it could be N. But then you get the coax. Eventually you have to go to an adapter. You can buy them online. You can buy them from me.
Okay.
We're prepared for that.
Thank you.
Sure. So, so you have a UV5 times 3 is what you have.
Okay.
Right.
Thank you.
You get the 2 meter 220 440, right? You've got,
Right.
I got a picture here.
Well, I've never got it working, actually.
You got this one here. You've got this one down here.
Okay.
So it'll say UV5 times 3. That means it covers 220. Otherwise, it's just called a UV5R, which is a dual band radio.
Oh, okay. I was wondering what that was. Okay, great.
It depends. I mean, if you paid $25 for it, you probably have the dual band. If you paid about $45 for it, you've got this tri-band.
Yeah, that's what I have. Okay.
Well, that's cool. Yeah, it should work. That's good. It's a great radio. We buy these. And they're cheap.
Oh,
enough.
yeah?
We buy them. I've got, because I'm the raffle chairman for like 3 clubs, so I just stock up on all this stuff. I'm not gonna every month figure out. I'll just buy all the stuff.
And you'll have.
Put it in storage, and then there's a raffle coming up. Then people always call me. I always got something. Again with
Ed, we've got like 4 other questions.
Sure. Okay, go ahead.
If we've got time. So, Scott, you want to ask your question?
Sure. Hey, Ed, real quick question.
Sure.
I noticed that you call for Schedule 20 PVC. Is there a huge difference with Schedule 40?
Correct.
What is there a huge difference?
Big difference.
Okay.
Again, the velocity factor.
Okay.
The more you put plastic around it, the more it's going to slow down the speed of light, and also the loss tangent to get up. Several reasons. That's one reason.
Okay.
We spec this out, and again, we recommend the lowest 23990 because it's the lowest loss tangent. Also, if you get the Schedule 40 at 3/4 inch, there's not that much room left inside for the antenna.
Got it. Thank you very much, sir.
That's why. So yeah, we
Don?
Yeah.
Hey, good evening, everybody, and good evening, Ed. I
Sure.
don't really have a question. I just was tell for those that are on the fence about this. Ed, I've been to Ed's house. I'm actually a volunteer with the Boy Scouts, and I've purchased Ed, I think mentioned he has radios. He has an antenna made for the 2 meter 70 centimeter, and then has a separate one is just for the MERS, GMRS, FRS band. And I gotta say, I've got one up on my roof now. It's been about 5 years. It has been problem free. We did some experiments with my scouts. And I can say that if you do use Schedule 40, I have a repeater with my club. It's in San Jose, and I live in San Mateo. And we could not hit the repeater for whatever reason using Schedule 40.
That's right.
But we use Schedule 20, no problem. So there is a little something that
we've tested. That's the advantage of having graduate students. We can do infinite tests for almost for free.
Well, and it's also a great thing that you're only like 20 minutes from my house, so I
come on down anytime.
And I need to come down. I need to get some more antennas.
Sure, anytime. Just give me a call. I think next quarter they want us back on campus, so I'll have less time at home. Right now, I'm always home. Yeah.
Dan, you want to go?
Just a quick, first of all, thank you, Ed, and
sure.
everyone for in the club that put this all together. We really appreciate it. On your shunt, your UHF shunt, on the DBJ1 and 2, I noticed that the shunt length of the RG174 stays the same. Earlier in the presentation, you held up an example of RG58, and it made me wonder whether you were using that RG58 in the DBJ 1 or 2 antenna.
Oh, no. Yeah.
Okay,
Actually, the shunt one, we use RG58. If you special order here, so you can see it better. It's used if you special order a 250 watt version, we have to use this. Obviously, the RG174 does not hold 250 watts.
so if one was to build your antenna using the RG58 instead of the 174 and trim the 58, you would start with a longer section of 58.
Yes, yeah.
And you trim back to tune the 440. Yeah,
Yeah, it's actually, and how to tune this thing. You read up the article we did in QST. I go by step of how you would do it. You do step at a time. You can't build it all at once because of all the mismatches and all. You take first step, get it working, and then you get the UHF section working, and then you add the stub. You know when you got the stub right is when the stub is right at the resonance, it's infinity, right? On one end, we short to one end. So what does that say? When I solder the stub in, let's say you have your network analyzer with the antenna working. When you soldered in and out, it shouldn't make any difference. In fact, you know when you in the ballpark, if the antenna is a little longer, let's say you have it at UHF resonating at 445 megahertz without the stub. If you add the stub and it lowers the frequency, that means the stub is a little longer than your antenna. If it raises the frequency, that means your stub is a little shorter. So you want it really to match.
Great. I built one. I had the pleasure of building one. Thank you so much for putting the article out there so that we can learn.
Did you get yours working?
I did, and my dimensions were a little off when I put the nano DNA to it and tuned it in, and you just mentioned everything that I needed to hear to know that we ended up in the right range. So yeah.
I mean, everyone says, "Oh, your dimensions are wrong." I never said they were right.
So RG58 will result in a higher level of power being able to run through that antenna then.
Right. That's how we make a 250 watt version. It requires different twin lead. It requires, again, a special made twin lead that can handle the higher power. Everything's special ordered. Believe me, everything is special ordered here.
Well, great. Well, thanks again. I'll be off on the side listening.
You're very welcome.
Thanks, Dan. Brian has a question.
Sure.
Brian, you want to come?
Yeah, good evening, Ed, and
Sure.
thank you for being with us this evening. I know most infeds have RFI feeding back.
Great question.
Points. So what are your recommendations for choking, ugly balun, a stack of toroids? What do you do?
So have you built a bunch of NFED antennas?
I have, yeah.
And did you require ferrites?
If I ran any amount of power, yes. Otherwise, the shack kind of, USB, computer functions, all sorts of things start.
See, I've got news for you. Then you didn't build them right.
Okay.
Again, my students, free labor, we did a bunch of tests. Yeah, that means the materials you made it out was running too high power. You saturated your material.
And I mostly do HF. I've never done anything, in-fed. So I was just wondering if these same things apply because
they apply.
We're working with multiband typically on the HF ones.
Yes. So you'll need ferrites.
Okay.
You come to my house. I don't have very many ferrites. I use ferrites are RF chokes, getting into my hi-fi and computers. I don't use them in antennas. And I tell you, we've played around these ferrites. This is my opinion. If you need ferrites to get your SWR low or whatever, RF out of the shack and things like that, here's my advice. That means your antenna isn't working right. It isn't optimized. Because if it is, all the power will be radiating from the antenna. So without all the math, I'm just common sense. If I have a really good working dipole, and you can do that, a dipole is 100% efficient. And let's say the SWR can get down to 1.2 to 1 or whatever. You can put a ferrite in the coax, right by where the antenna feed line is. And you can pump 100, 200 watts through it. And first you get the antenna working first, then you put the ferrite. Do you think the ferrite's going to get hot?
The core would if you have a mismatch.
Yes, no, I said, if you have a perfectly or closely matched antenna, 1.2 to 1, 1.3 to 1. So the antenna assumes to be radiating pretty efficiently. The power you're putting in is radiating. So now put a ferrite right by the feed point. Do you think it's going to get hot?
Shouldn't, no.
That's right, it won't. But as soon as you mismatch the antenna, very easy, just go up in frequency, 100 kilohertz, right? SWR starts going up to 2.5 to 1 or whatever. Then you put the ferrite, it does go down to SWR. Because where did that return power mismatch go? It went into the ferrite. And you probably experienced this, Brian. It can get really hot, right? Those ferrites, when you start transmitting 50 to 100 watts on a mismatched antenna, it can get really, really hot. I mean, I've had it accidentally where, whoa, that's too hot to touch. So when that's the situation like this, you got to fix your antenna. Why am I going through super duper high-tech MOSFETs, DMOS, bipolar amplifiers into my 7300 HF or my Collins S line to heat up a bunch of ferrites? I could put that on top of my stove and heat up a bunch of ferrites. So ferrites are good to suppress RF, like you're getting into your hi-fi, your computer. On the transmission line end, our philosophy is not that it'll hurt, but if you put ferrites in line, it's getting hot. There's something wrong with your antenna. You're saturating it. You're doing something wrong. I've experienced it. I know exactly what you're talking about.
InFeds normally use the feed line as part of a counterpoise. So how does the feed line length come into play?
Does not use it as a counterpoise.
It would not in your design.
It is not a counterpoise. It is an impedance matching. Here. This one. What is it really used as? It is not a counterpoise. It is matching the impedance of 0 ohms, which is a short circuit. It's a resonant transformer is what it is. And on the Smith chart, it says, if I feed it here, it's short circuit here, and if I look at the Smith chart, a quarter wavelength later, right? A quarter wavelength later, short circuit, quarter wavelength later, it becomes ideally infinity. In real life, obviously not infinity. It's thousands of ohms. You're not going to get real infinity unless you have some duplexers or something like that. So what happens is all it's doing is it's going and it's going from 0 ohms to, I wouldn't say infinity, several thousand ohms if you measure it. And what you're doing is you're tapping it. If this is 0 ohms and this is high impedance, well, that means you must have run into 50 somewhere, right? If you go from 0 and it's high here, where's 50? Well, it turns out in the VHF case, it's about 1 1/4 inch. So you got to find that tap point. That's what you're doing. It is a transformer. It's a resonant transformer. It's a transformer at a particular frequency.
Right.
And we're probably getting close to the time, and I think Rick might have his audio back for one last question. Rick,
So Brian, does that make sense?
In a way, I kind of work on InFeds more in an HF world where, you are using them on multiple bands, and it is a total compromise antenna.
Oh, it is.
That I throw up in a tree just because
Oh,
it's put up. And
I
don't use them at
field
home,
day,
but
use good resonant. The best antenna to get that's simple, I find, and I've done this for 55 years now, field day, 55 years. Of all the ones you try, a good resonant dipole, high up in the clear now, that's the key. High up in the clear makes the most contacts. We're talking about 67 feet. Get some good redwood trees, good antenna launchers, launch them up, hoist them up, good resonant dipole, and the dipoles, make sure they're resonant now. None of this wire tuner stuff. Works the best.
Thank
We
you.
made the most contacts on that. All this other stuff, like what you say, they're compromises.
Yeah.
So what I do is I'm a no compromise guy.
Thank you.
No compromise. And so we use the same dipoles every year. Once you get them going, we've used the same dipoles now for 20 years at the Sunnyvale Amateur Radio Club. The trick is get it high up, and we operate QRP and we make contacts. But you probably modeled end-fed antennas, these compromised. I mean, you lose 6 to 10 dBs compared to a dipole.
Right.
But again, get all bands, right? Can't have everything.
Right.
Can't have everything. It's tough.
Hey, Rick, are you back with us?
Rick.
Yeah, I think I got it worked
Oh,
out.
now I can hear you. Sure.
Yeah, I changed microphones. It seems to work a bit better. Now I know not to use that one anymore. Question I have was about your the tri-band
Yeah.
version
Sure.
and the helix antenna that you have on that.
Well, you'll have to call me
wait
on
to
that.
put it on. What?
You have to call me on that because this talk is on the dual band. I just don't want to waste people's time. But there's a quick question. Go ahead.
I was just wondering, how effective is that compared to the rest of, as compared to the half wave,
Okay, it's in the article. Do you have a copy of the QSC article?
I can get a copy of
Okay,
it.
I can send it to you. I'll be glad to send it to you. And we have a plot of it. And we had to do that on Fedco. Fedco simulated with the coils. And that was done at Northrop Grumman. They simulated that coil in that configuration. Pretty hard to simulate. I tell you, because you got the cable going through, but we did it. Steve Stearns, I think you guys probably know him. We stole some time at Northrop Grumman. And, where you lose is, I don't think you lose in the performance much. Oh, but I tell you, you do lose bandwidth. Compared to a dipole, we lost bandwidth for sure. But,
Well,
if it's resonant,
fortunately, 223 isn't 223 is not a really wide frequency
yeah,
band that I got.
it's you can adjust it. The bandwidth is just barely. We can barely get the bandwidth in there because compared to a dipole, with a dipole at 220 or 12 inches to the meat side, bandwidth is probably twice.
Okay.
So Ed, we're reaching the end of our time. Thank you very much for attending. We will look at future presentations on the chat room. Stay tuned.